today. Before we start, here are a few useful tips. This webinar is being recorded, and the record will be sent to you if you sign up. Second, you will be kept on mute during the seminar, but please feel free to ask questions using Q&A window. Questions will be answered as many as possible. If you have any feedback, please don't hesitate to let us know. You can tweet about the seminar with #Webinar. And I also encourage you to subscribe to the Webinar series as well as our newsletters to keep the Thieme chemistry information up to date. And the next webinar will also be taking place. And the details, please subscribe to our newsletter. And here I would also like to take the chance to briefly introduce you our journals and updates. Thieme is a German company with an international presence and over 130 years of experience in publishing science and medical information. Thieme chemistry products, you may already know, science of synthesis, pharmaceutical substances, and our journals such as Synthesis, Synlet, Organic Materials, ThinFacts, and ThinOpen. In particular, ThinOpen, a gold open access journal, has just received its first impact factor last year. And we have also expanded the scope of chemistry to other research fields. Last year, we launched a new open access journal called Sustainability and Circularity Now. It is an interdisciplinary journal focused on sustainability issues, and we have Professor Chris Sludvek as the editor-in-chief. The submission is now open. So let's go back to today's Thieme webinar, and we are very honored to have Professor Yefeng Tang as the chair of today's webinar. Professor Yefeng Tang earned his bachelor's from Lanzhou University and master's degree from the Institute of Material Medica, Chinese Academy of Medical Science. And then he pursued his PhD under the guidance of Professor Yang Zheng and Professor Chen at Peking University. Subsequently, he conducted postdoctoral research with Professor Casey Nicolau at the Scripps Research Institute from 2016 to 2009. In 2010, he commenced his independent career at the School of Pharmaceutical Sciences at Tsinghua University, where he is now a tenured professor. His primary research interests encompass the total synthesis of natural products, development of synthetic methodologies, and antiviral and anti-aging drug discovery. And now I will hand over to Professor Yefeng Tang, and he will chair today's webinar.
Okay, thanks, Yingchao, for the kind of introduction. And also, hello, everyone. Welcome to this seminar. And as you know, I'm very happy to chair the webinar today on biomimetic and net product synthesis. As you know, the concept of biomimetic has found wide application in organic chemistry, especially in the design and the development of catalysts and the total synthesis of net products. As an emerging research area, the biomimetic synthesis has attracted considerable interest from synthetic community in the past decades. To showcase the recent progress in this field, Professor Deng Jun and I have organized a special cluster of biomimetic and net product synthesis published in Synletter recently. So today, we're glad to invite three experts in the field of biomimetic chemistry as a speaker. As you will see, their research focus are very diverse, ranging from the molecular assembly, the total synthesis of net products, and the computational chemistry. I believe all the audience will benefit a lot from their talks. So now I will go to the first speaker, Dr. Jack Chen from the Department of Chemistry, Auckland University of Technology. I will give a brief introduction to his education background. Dr. Jack Chen received his PhD from the chemistry department of University of Auckland in 2010 with Professor Margaret Brimber. After a postdoc stay with Professor Virender Agawa at the University of Bristol, United Kingdom, he was introduced to supermolecule chemistry in the group of Leonard Prince in Padua, Italy. After that, he started his independent career in the School of Science at Auckland University of Technology. Jack's research mainly focused on the making some functional molecular architecture based on molecule self-assembly and cooperative effects. Today, his topic will focus on the biomimetic catalyst system from the self-assembly of amphiphiles. Please welcome Jack Chen.
Thank you very much for that kind introduction. Can everyone see my screen? Is that clear?
Yes.
Yeah.
Okay, perfect. Thank you. Yeah, so hi everyone. Yeah, my name is Jack Chen, and I lead a research group at Auckland University of Technology in New Zealand. I'm also affiliated with the University of Siena, where I have a smaller group of research students. And our research interests span essentially organic synthesis to stimuli responsive materials. And today I'd like to talk about our work on some bio-inspired catalytic systems formed from the self-assembly of amphiphiles, in particular studying their cooperative properties and taking advantage of their dynamic nature to create some stimuli responsive systems. So much of this work has been inspired by the ability of enzymes to place specific functional groups in precise orientations within an active site, so that they're able to work together and cooperate to drive chemical reactions. Here we've got the classic example of a catalytic triad consisting of serine, histidine, and aspartic acid residues within the active site of chymotrypsin, which then work together to cleave an amide bond. It's important to note that each of these functional groups on their own is not able to achieve this, but together, working in a cooperative way, nature is able to achieve this. And so synthetic chemists have taken inspiration from these natural systems and tried to recreate these enzymatic pockets within artificial systems. Examples include taking the key functional groups required for catalysis and placing them onto molecular scaffolds like glycerines or onto dendrimers, or attaching them onto the surfaces of nanoparticles. And a lot of the work in this area has focused on the creation of rigid pre-organized structures or pre-organized systems. And what we've been doing in our group is to use instead hydrophobic interactions to try to induce cooperative interactions between different functional groups to create catalytic systems that are able to perform interesting chemistry. So our substrate of interest has been this phosphodiester, HPNPP, which has been commonly used as a model for RNA cleavage. And this is an ideal substrate for our studies because its cleavage has been shown to involve a cooperative mechanism where two zinc binding units essentially are required to be placed in close proximity, with one of the zinc ions binding to the phosphate, making it more electrophilic, and the other one stabilizing this internal nucleophile, this alkoxide, which then goes to perform an intramolecular transphosphorylation to form this cyclic phosphate with paranitrophenolate as a side product. And so the formation of PNP here allows these reactions to be monitored quite easily because it's yellow, so you can use UV spectroscopy to follow the course of the reaction. So what we have done is essentially taken a zinc binding unit Okay, so a metal chelator, and a very famous one, that TACN, and this is a let's say metal chelator that has been made famous by a number of researchers because they have employed this in a lot of nano enzymes. Okay, so enzymatic systems that have some biomimetic characteristics. One of which is Paulo Skrimin, who's worked a lot with these TACN complexes. So what we did was we took TACN, we essentially attached a hydrophobic chain to generate an amphiphilic molecule. And what we noticed is that at low concentrations, so concentrations below the critical aggregation concentration of TACN, we see low catalysis, and that's due to the fact that these molecules are not assembled. Above, however, the critical aggregation concentration, we see the formation of vesicular structures, which we can also image using TEM, transmission electron microscopy. And when this occurs, we allow the formation of these catalytic pockets on the surface of the vesicles that places two of these TACN units together in close proximity, which allows cooperativity between them and the cleavage, therefore, of HP and PP. Now, these systems are interesting because they have a lot of characteristics that are very similar to enzymes. So, for example, if you measure the reaction rate, as you can see in the y-axis, with respect to the HPNP concentrations, the substrate concentration, you get these Michaelis-Menten saturation kinetics that are characteristic of enzymatic systems. And this gives support to the fact that we have essentially catalytic pockets that have been formed on the surface of these vesicular structures, and that can be saturated with increasing substrate concentrations. What we've also shown is that there is cooperativity between neighboring groups on the surface of these vesicles. And how we show that is by essentially plotting a curve of the rate of reaction here, again on the y-axis, versus the amount of zinc equivalents that we add into the system. We can see that at low concentrations of zinc, here from about 0 to about 0.3 molar equivalents, even though we're increasing the zinc concentration, we're not seeing a great increase in the catalytic activity. And that's because when the zinc incorporates itself into the vesicular structure, they're able to occupy spaces that are really distant from each other, okay, because of the repulsion between these zinc ions. But as we increase the concentration, okay, now closer to 0.5 molar equivalents, the zinc ions have no choice but to be next to another zinc ion. Okay, so you're forcing them to be next to each other. They then are able to form these catalytic active pockets and cleave HP and P. As we increase the concentrations even more and approach 1 equivalence, you can see that the increase in the rate slows down, and that's because we start to saturate the surface of these vesicular structures. And so this kind of sigmoidal curve is indicative of cooperativity between these functional groups. What was perhaps even more interesting is that we noticed that the critical aggregation concentration actually changed depending on the substrate concentrations, the concentration of HP and PP. We can see that at a concentration of 0, HP and PP, the CAC of the system, okay, is close to 100 micromolar. So that's 100 micromolar of this amphiphilic molecule, okay, with zinc. And you can see that as we add in HP and PP, you can see the concentration increase here on the x-axis. That CAC dramatically decreases, okay, so that at 1 millimolar, the CAC now is close to 10 micromolar, okay. And what that's telling us is that the addition of the substrate is actually inducing the formation of these vesicular structures. So we can start with a disassembled, essentially state, add the HPMP. The HPMP induces the formation of essentially the catalyst, which then breaks it down. Okay, so it's an interesting example of a substrate-induced formation of the catalyst. And that again is an analogy to natural systems where a lot of enzymes, for example, are formed just when it's needed, and then it can also be broken down when it is not required. It also has close analogies to dissipative out of equilibrium systems, which is now a huge and exploding field in the area of systems chemistry, which essentially discusses the fact that in a lot of natural systems, we're operating here in a dissipative state, which requires a constant input of energy to maintain in a structurally viable functional state. If we essentially run out of energy, that means we'll go down, okay, to the equilibrium state, which means essentially a system will die. So a biological system will die if it runs out of energy. It requires constant input of energy to stay here in the dissipative state to maintain, for example, the metabolic processes. And so our system has analogies to that again. So you can think of HP and PP as a chemical fuel, okay, which is used to then form these structures, which then has a particular function, which is to break down the fuel which induced its formation. Now, this system is not completely dissipative because we found that in our products, okay, so our side products are also able to induce to some degree the formation of these vesicular structures. So it's not a perfect system, but it goes into some way into recreating these fuel-driven self-assembled structures that are so prevalent in nature. If you want to learn more about dissipative self-assembly and fuel-driven self-assembly, there are two very good reviews here by Ragazon and Prinz. So can any of these systems actually have some kind of synthetic utility? Can this idea of the self-assembly of amphiphiles be used to make synthetically useful catalysts? Well, in theory, this concept would benefit any reaction that requires two catalysts to act cooperatively. And the classic example of such a reaction is Jacobson's hydrolytic kinetic resolution of epoxides to generate these enantiomer-rich epoxides. In this reaction, we have essentially one cobalt ligand, one cobalt center, which binds to the epoxide, making it more electrophilic. And then we have another cobalt complex, which stabilizes the hydroxide ion, so stabilizes essentially the nucleophile, which then goes to attack and open up the epoxide. Now, Jacobson and several others have explored several strategies to enhance the cooperativity, okay, between these two catalytic units, including attaching the silane complexes into dimers or oligomers or polymers, and as well as onto molecular scaffolds or onto nanoparticles. And what we wanted to explore was the possibility of enhancing cooperativity by utilizing hydrophobic interactions. So we synthesized a number of analogs of this commercially available silane complex. What we essentially did was we added two tails, okay, onto the two aromatic ends of the silane complex. We made a number of variants, so a C8, a C12, and a C18 variant. And what we found was significant increase in activity. So we can see here with the C18 variant, okay, here the essentially the chiral resolution of epichlorohydrin is complete within 30 minutes, okay? And whereas if you look at the reaction with a commercially available catalyst, the reaction still wasn't complete after 5 hours. And we see essentially a correlation of the reaction rate with the length of the chain that we attached onto the silane complex. Now, to get a bit of insight into what was driving this increase in reaction rate, we compared essentially the K-obs, okay, of the control, so with a commercially available reagent, as well as our catalyst, the C18 variant. We first conducted these studies under homogeneous conditions. So we added THF to make sure everything was homogeneous. And under these conditions, though, we saw just a 4-fold increase in reaction rate. Okay, so whereas in the example before, we saw roughly a 10-fold increase in reaction rate. Now, under these homogeneous conditions, we saw that this reaction rate increase was proportional to the length of the chain, so directly proportional to the length of the chain that we added onto the saline complex. Then we went back and looked at the reaction again more carefully, because the reaction itself is actually a biphasic mixture. Okay, because here we have epichlorohydrin under solvent-free conditions with the reagent, which is water. Okay, so we've got a biphasic mixture essentially of epichlorohydrin and the water. And we see that under biphasic conditions, the K-ops is actually increasing, and essentially the rate, actually the times of improvement of the reaction rate, of the catalytic rate with our C18 variant actually increases with increasing concentration of the catalyst in solution. And so we thought that it likely has something to do with the ability of our amphiphilic molecules to also stabilize the interface, okay, stabilize essentially the emulsions that are formed during the reaction. And we were able to confirm this with dynamic light scattering that looked at the size of the droplets, essentially the droplets of water inside the biphasic mixture. So we can see here, in the absence of any catalyst, the droplets are essentially much greater than 1 micrometer. In the presence of the controls, the commercially available catalyst, these droplets are close to 1 micrometer. But in the presence of our C18 variant or derivative, we get much smaller droplets, which means that we're increasing the interfacial area, and that is another way in which we are increasing the reaction rate in these biphasic systems. And we think now, so with the increase in green chemistry methods, with a greater interest in reactions at the interface and on water catalysis, for example, potentially modifying some catalysts into amphiphilic species could be an interesting way to provide more efficient catalysts with activity at the interface. Now, so far, the reactions, the examples that we have seen have involved cooperativity between two essentially of the same functional groups. So we're inspired by this example here. So this is going back to the HPNP, okay, as our model compound. We see this example here, and it was able to combine two different functional groups and again show cooperativity in the cleavage of HPNP. So in this system, by Casanati, they combined a zinc binding unit with a guanidinium. Again, in this case, the guanidinium is activating the electrophile, and then we have the metal again stabilizing the nucleophile. And so our idea was reasonably simple: was can we self-assemble amphiphiles containing these two key functional groups that are required for this reaction? So we took the same TNCN-based amphiphile, we also synthesized a guanidinium-based amphiphile. And this now, I think, goes to illustrate really one of the strengths of this modularly assembled system. The molecules, first of all, are synthetically quite simple, okay, much easier to synthesize than, functional groups that are embedded onto a molecular scaffold. And we're also able to easily vary the proportions of these two amphiphiles to investigate potential mechanisms for the reaction. Here on the far left, okay, so we have essentially 100% of this TACN-based ligand. On the far right, okay, we have 100% of the guanidinium ligand, and on the y-axis we have the catalytic rate. So we can see that at either end, 100% TACN or 100% guanidinium, we have relatively low reaction rates. But we see very strong evidence of cooperativity. So as soon as these two amphiphiles are combined, we see an increase in the reaction rate, which peaks at a ratio of 1 TACN to 2 of the guanidinium-based ligand. And this is quite powerful because this kind of variation, the proportions of the two ligands, is not possible or is not easily feasible with functionality that are embedded onto a covalent scaffold. So this is another advantage, I would say, of these modularly assembled systems. So with this system, we were able to essentially conclude that our 1-TACN to 2-guanidinium system gave us the optimum catalyst. And then we went on then to measure essentially or determine the catalyst Benton parameters for 3 systems, a 1-2 TACN guanidinium system, as well as a 1-3 and a 1-1. And this was interesting because we can see that the 1-1 system has a significantly higher Vmax compared to the other systems, which suggests that it is stabilizing and forming potentially a different transition state compared to the other systems. We also show that these systems are highly dynamic. So we can start off here with a 4-to-1 system. So this is showing now the reaction progress over time. So we can start off with a 4-to-1 TACN to guanidinium system, okay, then increase or add more of the guanidinium species to then form a 1-to-3 system, and we see a rapid increase, essentially in situ formation of a different catalyst and an increase in the reaction rate. We can also start off with a more active system, a 1-to-3 TACN guanidinium system, add more of the TACN, and that will again re-equilibrate itself, reconfigure itself, and form a less active system. And currently, we're exploring the modular formation of other types of biomimetic systems. We're combining different, again, amphiphilic molecules now to look at esterase activity. So this is using so now paranitrophenol butyrate as a model activated ester substrate. And in the system, we've shown that we can have combination of these 3 key functional groups. And this is our most activated, most effective system. And to start off with, what we did essentially was to make different amphiphilic variants that are representative of different amino acids that are commonly found in the active site. So like a histidine-based derivative, an amphiphile that's similar to aspartic acid, now another amphiphile that's similar to serine. And the power of this kind of methodology is you can mix and match, okay, different combinations, okay, to then very quickly screen different these different combinations and come up with a let's say a lead system. So our initial lead system was a 1-to-1 combination with histidine and guanidinium. We further did other iterative screens by combining other amphiphilic molecules, and we ended up with an optimized system of a 1-to-1-to-1 histidine-based, guanidine-based, and a dipicolyl-amine-based system, amphiphiles, where we've come to the conclusion that in this optimized system, most likely we have the guanidinium activating the ester, okay, and the histidine-based system acting as a nucleophilic catalyst. Then we have a second step where we have these zinc binding units that are able to stabilize hydroxide anion and then act as the final nucleophile to cleave the ester. Cool. Now we wanted to conclude in the last few minutes and conclude looking at us trying to make use of the dynamic nature of these self-assembled systems. So in our system, essentially, we have formed a functional assembled structure that has an emergent property, which is essentially catalysis. And so the idea is, because these systems are being formed by reversible interactions, if we can actually control structure formation, we should essentially control also the catalytic property that is inherent or inherent property of self-assembly. And so the idea was to incorporate a photoresponsive element into the amphiphile that we have been working with. So here we've got essentially that similar amphiphile with a catalytic head, okay, and embedded into the hydrophobic chain, we put this azobenzene unit. Now this diazobenzene has been used in a lot of photoswitchable systems, and the trans or the E form of these molecules are able to pack really closely together with each other. On the other hand, when we're able to use UV light to switch this to the cis form. The cis form, however, has a little bit of a twisted structure. The reason being, you've got steric hindrance here. Okay, that doesn't allow these two aromatic rings to be completely flat. And the idea was that we could control self-assembly by switching between the E and the Z forms, okay, of this amphiphilic molecule. The E form should be able to self-assemble very efficiently to form the vesicular structures, which then allow these catalytic heads to be close together. We can turn on catalysis. Then we should be able to switch these molecules into the Z form using UV light. And these should pack much less efficiently. And we can then use control essentially of structure formation to turn on and off catalysis. So this was the grand idea. And we're able to follow the switchability between the E and the Z forms of these molecules, so by UV as well as by NMR. We can see here that the photostationary state of the majority E form has 80% E form, about 20% of the Z. But we're able to switch almost completely to the Z form, about 95.5 to the Z form. And we can do the switching over multiple cycles, essentially without photodegradation. And the key thing is that we were able to show that the rate of catalysis also changed when we switched between the E and the Z forms. In this diagram, we have the rate of reaction x-axis, and we've got multiple cycles, so in the y-axis, and multiple cycles in the x-axis. We start off with a high reaction rate. We're able to switch down to a lower reaction rate using UV light, okay? And we're able to reversibly switch between essentially higher activity and lower activity. So this system obviously isn't perfect because we can see that there's significant amounts of activity even in the Z form, and it's because we believe there's still some degrees of assembly that can happen even when the molecule is in this form. But it was a nice demonstration that you could use control of structure formation, okay, to essentially control catalysis. So that's me today. So in summary, we've shown you some examples of amphiphiles which could form the vesicular structures that are induced by the substrate. And these have implications for dissipative and out of equilibrium systems. We've also shown the power of these amphiphilic molecules in that they can be modularly assembled to investigate the mechanism of the reaction, as well as to really quickly optimize a new catalytic system. And hopefully this can be used to, in the future, find novel combinations between amphiphiles for specific reactions. And finally, I showed you an example where we can actually use these photoswitchable variants of these amphiphiles to form stimuli responsive systems. It remains for me to thank obviously the students that actually did this work, the main students that worked on this on these projects that I presented today were Pablo, Chloe, and Olivia. Thank you also to my key collaborators, the funding agencies that have been very, very supportive in New Zealand. And thank you, all of you, for your kind attention. If there are any questions, I'm more than happy to answer them.
Okay, thank you, Dr. Jack Chen. And I think we have some questions from the audience. Let me see. The first one is, what's the difference of this work compared to conventional micellar catalysts? This is the first question. Yeah, you
cool.
can.
That's a really
Yeah,
I'll go to some slides that maybe can help to demonstrate this. No, this is a very good question because that's a question that I get asked a lot. So with traditional micellar catalysis, first of all, usually we're dealing with reactions that occur in the hydrophobic, let's say hydrophobic pocket of micellar or potentially even vesicular structures. Here we're dealing with reactions that are occurring essentially at the interface, okay, between water and, let's say, the oily parts of the molecule. And also, I mean, quite a bit of work has been done in the 80s and 90s, also looking at functionalized amphiphils, okay? So even also reactions that are occurring essentially activated by the polar heads of these amphiphils. But few studies have actually looked at cooperativity between neighboring groups, okay? So that's essentially the key advantage here is this idea of forming catalytic pockets between different functional head groups, okay, which is the key novel part of this work.
Okay, so the second question is, what are the disadvantages of your system? You make use of the dynamic nature in your system, but can this also be a disadvantage?
Yeah. So I mean, these dynamic, as I've shown the advantage of the dynamic systems, but there are also key disadvantages. One is obviously because it's dynamic. If you add, for example, other amphiphils or other systems that can interfere with the self-assembly, you can get systems that are very hard to characterize. And you don't know what are the key molecules that have essentially been assembled. What we would propose, let's say, for this kind of work is to use these amphiphilic systems, okay, as a way to do an initial screen to see what functional groups are potentially interacting, okay, similar to what I showed here. And then to hopefully come up with novel combinations of different amphiphils, different combinations of different functional groups that can be involved in activating catalysis. And then if needed, to actually form a stable catalyst, you would actually immobilize them onto a substrate, okay? So that's probably still the best way to form let's say, a stable and useful catalyst, is to mobilize these catalysts onto a substrate. But what we would suggest is that this kind of these amphiphilic systems are really useful for the modular screening and optimization of the system prior to then potentially immobilizing them to form a stable, useful catalyst.
Okay, here's another question. What can the last switch, photo switch catalyst can be applied to what kind of reaction?
So this specific one, so this example here is still using essentially the two zinc head groups together. So we're still cleaving HP and P. So this is still, again, just a model reaction. Yeah. But you could add different functional groups onto these heads, okay, and so that you can potentially turn off and on a different reaction. But so these kind of systems, I mean, the stimuli responsive system probably isn't very useful, let's say, for inventing new catalysts, but is very interesting in the areas, for example, of systems chemistry, where they're interested in how essentially different assemblies or different systems can interact with other systems. What we would like to, let's say, go ahead, what we'll do in the future with these kind of systems is to actually use the system to turn on catalysis, which then produces, let's say, a product which is able to do something else, okay? So essentially form complex chemical networks that now is a very important field in systems chemistry.
Okay. So I just have a very general question for you. I noticed that your education background is very diverse. For PhD, you are working on the photosynthesis lab, and for your postdoc, actually the Agua is a methodology guy, and then
Exactly.
postdoctor study you work on supermolecular chemistry, right? So
exactly.
I just wonder, how can you change from one research field to another so smoothly? And do you have some challenge? How do you address it?
Oh, definitely. I think when you go to a new research group, is also always a challenge because you're always joining a research group where, which is full of experts in that area. So you always feel behind, and you're driven to then catch up, and then you learn. I think the key is to be flexible. I would say in my training, total synthesis, I think, was an amazing way to let's say be trained in organic chemistry, to be familiar with a huge range of organic reactions. And I was actually really happy to move from total synthesis to methodology because it has a completely different aspect, right? Because now you're focusing on a specific reaction. You want to look really deeply into the mechanism and how the reaction occurs with a completely different focus. Okay. Yeah. But yeah, no, I love that. I love the different aspects of organic chemistry. Supramolecular chemistry is very different again, and I would say, and I think as you can see from this talk, maybe the focus now is more on like new concepts, new ideas, rather than the traditional synthesis and making molecules. Yeah. So no, I've really enjoyed this journey. I'd say the key to, let's say, surviving, I would say surviving rather than being successful, is to be flexible and have an open mind and be willing to learn.
Okay, so maybe we should stop here for the time limit. Thank you for your wonderful talk. I think the audience will learn a lot from your talks.
Thank you so much. Thank you for having me.
Okay, so next we will welcome the second speaker, Professor Chen Tang, right? Okay, let me have a brief introduction to Professor Chen Tang. Professor Tang obtained his PhD degree with Professor Gary Patton at the University of Nottingham, United Kingdom, working on the biomimetic synthesis of complex polycyclic diterpene. After postdoc work with Professor David Harrowing at the University of Southampton, he joined the Professor Patton's group in the University of Oxford to focus on computational study of biomimetic synthesis of net products. Professor Tang started her independent career at the University of Nottingham, Ningbo, China in 2014, where he is now an associate professor. Her major research focus is to explore the biomimetic synthesis of marine net products, both computational and experimentally, as well as artificial intelligence assisted drug discovery. So today, our topic will focus on the application of quantum chemistry in biomimetic synthesis of polycyclic furanol membrane derivatives. Welcome, Professor Tang.
Thank you, Yefeng, for the very kind introduction. And thank you and the organizer for giving me this opportunity to present our work. I'm currently based in the University of Nottingham. So my journey in this area started a long time ago when I was doing a PhD with Professor Patton, as Yefeng just introduced. At that time, I was focused on the synthesis of those two nature products, and as we can see from the structure here, both of them are with very complex structures. They are highly oxidized and with multiple sterogenic centers. So they are quite challenging in terms of the synthesis. And at that time, my supervisor, Jerry, and another few leading synthetic chemists proposed that intracarine could be derived in nature from biphenylating J through those transformations here. So first biphenylating J could be converted into this 18, which has a indiol system here, and then this can be converted into 19, and then after losing a molecule of water, and this dipolar, or this species 20 can have a transannular 5+2 cycle addition reaction to lead to intracarine. And so this we actually realized in this in laboratory using the synthetic sequence showing here, and the only sterile chemistry product we isolated is actually intracarine. And at the same time, there are other groups like Professor Chona also published this work. So that's the synthesis, and then not soon after that, Professor Tantillo published a computational study of this reaction, showing that the endo, so the endo transition state, or the transition state leading to the endo product, which is the intracarine, is indeed with lower energy than that for the exo transition state. So this is pretty much the first time that I saw the computational chemistry being applied in the natural product synthesis. And interestingly, then later on, Chona Group published another work towards the synthesis of intracarine, which is a photochemical formation of intracarine, following similar sequence, but is initiated by photo excitation. And they also carried out this fantastic computational study of this full transformation sequence. So this caused us to think about a question. We want to ask that how much can computational chemistry help with the biomimetic synthesis of natural products? With the development of the software and the hardware in computer, and actually computational chemistry is playing a more and more important part in different areas of chemistry. And at that time, actually not many people believe that the computational chemistry can make any decent computation, an indecent contribution to the synthesis of natural products. Because for the synthesis of natural products, you got to make compounds in laboratory. Just by doing computation, it's kind of hard to convince people. Well, we got interested in this by looking at more natural products in this area. As we can see here, that the providencin has this kind of 4-membered ring, and this is another one. Plumerilide has a 6-membered ring together with these two mendepimate and isomendepimate. They also contain 6-membered ring. And interestingly, the remersvarilide contain a 7-membered ring. And these compounds, as well as the biomimetic synthetic proposal, are well documented in those review papers. And these were proposed to be generated from those simple furan membranes through various pericyclic reactions, right? Through various pericyclic reactions here. And also, the computational chemistry regarding, or computational chemistry relevant work in computational chemistry and nature product relevant review paper written by these authors can also be seen here. So there is an interest here. So we set off our journey from bioshelf sequencing. Bioshelf sequencing was proposed to be formed from bipyridine J through a 2+2 cycle addition pathway in which the bipyridine J can be oxidized into this 21, which after a furan dearomatization can be converted in 22. And this 22 is beautifully set for a 2+2 cycle addition or to form bioshelf sequencing or via a stepwise pathway involving a micro addition, then followed by an aldo reaction to form this four-membered ring. Then after ring closure here, we can get a bioshelf sequencing. So with Rob, Professor Payton at that time at Oxford University, we carried out the investigation in this. From our calculation, we predicted that the photochemical formation of bioshelf sequencing is almost with no barrier. And to our delight, the recent publication from West and Roche, they show that on this substrate 8A, irradiation with light, that the 2+2 cycle addition indeed can happen through this intermediate here. So then we tend to look at a different natural product, providencin here, which is isolated in 2003. And it contains this butanol moiety, which is proposed to be generated from bipyridine E, which has a carbonyl group here. So all those three natural products were isolated from similar coral species. In the synthesis, in the proposed biosynthetic pathway to providencin, a photochemical ring formation reaction was proposed. Firstly, this carbonyl group here can be excited, this N-pi excitation to form this diradical, and then after a 1,5 hydrogen abstraction, we can get this diradical, which can then have a ring closure process to give providencin. So with Rob, we carried out a computational study for this process. Firstly, we calculated that the excitation of this carbonyl group can happen at the light at this kind of wavelength 310. And then after the 1,5 hydrogen abstraction, we can get this intermediate INT6. This INT6 can then have the ring closure reactions potentially leading to 4 different diastereoisomers due to the rotation of the carbon-carbon single bond here. And through our calculation, we suggest that we could make the suggestion that leading to providencin is the most possible or most feasible pathway among the 4 because of the rotation of the carbon-carbon bond due to the steric hindrance around that area is difficult. So we predict that the providencin should be the product formed. So the stereochemistry in providencin should be the stereochemistry from this transformation after the ring closure process. So we made a conclusion here, right? So this process is possible and the stereochemistry should be the one we would like to see in the providencin. And we were very delighted to see this paper published by Roche and West that they irradiated by P19 E, they did get providensin, no other diastereoisomers from the publication, and also a residual isomer, which is close or reacted on this carbon. It's a carbon 14 on the ring. So this inspired us to think about another question that do we want to be more brave? We want to think about, or can we think about using computational chemistry to guide or to orient the biomimetic synthesis of nature products? So we decided to take those 3 nature products as a trial for this question or for this idea, that these 3 nature products were isolated from similar coral species. They got this complex structure and highly oxidized and so on. So in the proposal to the formation of mendempamate and isomendempamate, that a 4+2 cycloaddition from this intermediate 43 was proposed. And this could be generated from a simple furan membrane such as 42, or a ring-closed form of the butanolide here. And the remsvarilide could be generated from a simple furan membrane here, 42B, by these transformations through a 4+3 cycloaddition reaction on this substrate. There are questions arises from this. Firstly, the dearomatization process. This is an important process because the geometry here of this double bond could influence the stereochemistry of the product. The cycloaddition process are also important because if it's a stepwise process, then the stereochemistry will be controlled by the geometry of the double bonds. If it's a stepwise process, then the stereochemistry in the product, especially in this carbon, wouldn't be influenced so much from the geometry of this double bond. Because clearly making a 14-membered ring with a trans double bond here or with a trans double bond here is going to be more challenging than make a 14-membered ring with a cis double bond there. So we think we could use computational chemistry to first to understand the dearomatization process. The dearomatization process involves using a diol here or an hydroxyl group here on the C7 position or an epoxide here on the C7 and 8 position here, causing the ring open of the furan ring, leading to this oxonium ion species. We want to understand whether or not the stereochemistry here or which of those groups here could influence the geometry of the double bond here. And we also hope to use computational chemistry to understand the pericyclic reaction that firstly, we want to understand if this is a concerted mechanism or a stepwise mechanism. Secondly, we want to understand, or we hope to understand, which would happen first. The cycloaddition reaction could happen on this substrate, for example. It could happen on this substrate after the nucleophilic attack from methanol, for example. And for these two, the pericyclic reaction could happen with the ring closed form or ring open form here. With the ring open form, this macrocycle would be more flexible. With the ring closed form here, this macrocycle would be less flexible. So those might influence the result, stereochemistry outcome of the cycloaddition reaction. And in the Ramsvarelite formation, the biomimetic synthesis proposal is from this oxonium ion that it can catch a molecule of water to become this intermediate, which then can have a ketyl and enol equilibrium conversion to give this 20, and which then can the double bond isomerize, this double bond isomerize to give you this intermediate, and then either stepwise or consecutive 4+3 can happen to form Ramsvarelite. And along this journey here, actually, there are also other possibilities. Firstly, both these substrates and all those substrates are they contain the diene and the dienol part for the 4+2 cycloaddition to happen, to give you these different ring systems. And that is actually indeed what happened in the mandempamate and the isomandempamate case. In those cases, the ketyl and enol, or the ketyl and enol equilibrium cannot be possible because you have a methoxy group here instead of a hydroxyl group here in those structures. And so those could be the other pathways on our way to form this Ramsvarelite. So I would like to understand which is the most possible pathway. Hence, we can consider how to design our precursor for the synthesis. We also want to understand that the stereochemistry outcome, what is the controlling factor for the stereochemistry required in the natural product. And indeed, in Jerry's model study, early on in Jerry's model study, when the cis double bond here used here, when this substrate is treated with the acid, that this desired compound couldn't be isolated or is not observed or is not absorbed. And what was generated was actually this ring system. It's due to the 4+2 cycloaddition between these two carbons, so between bonding between these two carbons and these two carbons. So that's indeed other possibilities are possible. So we are actually making submissions for publication for this work. So, but in short, we'd like to share that through our calculations for the formation of mandempamate and the isomandempamate, we'd like to suggest that the ring formations for both are from stepwise processes. And either an epoxide or a diol introduced here wouldn't make a difference for the ring for the whole sequence. And also the mandempamate and the isomandempamate, they could be generated from the same precursor, but with different conformation. And those conformers are interconvertible conformers. And for the Ramsvarelite, our calculations suggest, so this is a very summary slide, our calculations suggest that the Ramsvarelite formation can be possible from this furan precursor 31, which after the which after the dearomatization to this 33, and then reopening to this IN51, and then conformer change to IN52. And from our calculation, actually, we didn't see that a double bond isomerization would be very necessary before the formation of the RAMS virolide. So if the calculations serve us correctly, we are confident that, our next step and what we are doing now is the synthesis of those two precursors. So this one is an unknown furan sembrane, and this is a molluscine E reported in 2018 by a research group in China. And this compound is actually synthesized by Professor Donahoe group in 2022. So currently, we have Zhou Tao and Wang Rui working on the synthesis of those molecules, and Wang Di working on the computational chemistry. And we hope that we can have a bigger team on this. We feel like we have a lot of exciting things to do. And Jerry took me in this area as a PhD student, and Rob taught me computational chemistry, and now Professor Hurst in the University of Nottingham, we're working together, supervising PhD students and so on. And Professor Gao and his team in Ningbo Tech University, we are collaborating in the synthetic part at the moment. And we have been very lucky to get funding support from different parts in the past years. And without the effort of all these students, nothing could be done. And then a little advertisement. We recruiting students every year. Thank you. That's for me. Thank you for listening.
Okay, thank you for your very nice talk. And actually, from your talk, we can see computational chemistry actually can provide very useful guidance for the design of biomimetic synthesis. Okay, we have several questions from the audience. The first one is, so for the West synthesis, I noticed that they made some modification on the substrate. So there is any explanation about that?
Modification on the substrate?
Yeah, West synthesis.
Okay, yeah. The photo, the Bioshovsky one, right?
I think there is West synthesis. Which one? Let me see. This is West work. Yeah, this work. So
this one.
I guess the audience may ask why they made some modification on the substrate. Not exactly the same as to the natural substrate.
Yeah. I think it's I think the original intention is probably that you introduce this carbonyl group here, when then presumably you can reduce and eliminate to introduce the double bond. No, hang on, not that one. Yeah. So you mean this substrate is different from what's required? Well, this work, right? In this work, I think in the Bioshovsky thing, you need a oxygen here. It's AC toxic group here, right?
Yeah.
So probably I guess that they want to introduce that here through this group.
Okay, that means the position of the oxygen functionality have not much influence on the 2+2 cyclization reaction.
Probably not. This because it's so if you got a OAC here, so this part here, I think they will not change the ring string much. Although
Okay.
this is a sp2 hybridizer carbon, if it's an OAC group, it's a sp3 hybridizer carbon. It's probably the sp3 one. With the sp3 one is slightly more flexible, but it will probably not make a big difference in this 14-membered ring.
Okay.
Yeah.
So we have another 3 questions. Let me see. The first one is during the isolation process, the collected carrots could be dried under the sunlight or upon heating. So is it possible that these net products could be generated during this process?
Yeah, I think this was it's actually a very interesting question. So these corals they generally live in shallow water.
Okay.
Yeah, so they are not in the deep sea, so they have sunlight in their lifetime, and also in the isolation, it could be possible, I think, for some of the nature products to be transformed into other forms. Yeah. And I highly doubt like the mandepamate, you have this open ring form of the butanolide, and if you use methanol in the isolation process, that could be generated in the isolation process, I suppose.
Yeah, I guess the audience maybe want to know if these net products, at least part of them, are actually artificial compound from during the isolation process. Yeah, it's possible. Yeah, it's possible. So the second question is what are the functional and let me see. What are the functional and the basis set do you normally use for these calculations?
Yeah, so these are carbon and oxygen and hydrogen based molecules, and we generally use like B3 leap, functional B3 leap, or AM06 X, those kind of functionals. And for B3 leap is without dispersion. We would add the dispersion in our calculation also. And for the basis set, we generally use a small basis set in the structure optimization, and then we use a larger basis set as well as the solvent model. If we don't use the solvent model in the structure optimization, in the energy calculation. So this has an assumption that the energy surface for when energy surface when you use a larger basis set or different functional in your single point calculation would be parallel to that the energy surface when you use like B3 leap and the smaller basis set in your structure optimization. In the structure optimization, we try to get the best. We try to get the best result from the lowest computational cost. In a single point calculation, then we can use a larger basis set. Generally, that's what.
Yeah. I think there are another question related with this one from the audience. That is, could you please introduce the computational software? Is it free for us?
We use Gaussian. And Gaussian is not, it's a commercially available software, but I think Gaussian is with a very nice price. Compared to other software, I don't want to compare, but you know which ones that Gaussian is quite friendly. They don't charge much.
Okay. The last question is, in the biosynthesis of mandapamate and isomandapamate, is it possible that the butanolides could have a ring-closed form in nature, and the ring form is generated during the isolation process?
Yeah, that's what I'm doubting that this could be the ring closure form in nature, because the hydroxyl group and the ester group, they are spatially so close here, right? In nature, and it could be the closed form in the nature species.
Okay, that means the butanolides is maybe somehow very strained, and during the isolated process, maybe some nucleophile can open this ring.
Yeah.
Okay. Yeah. So I just have a very general question about this work. So do you think there are any enzyme involved in the biosynthesis of this polycyclic net products? As you can see, a lot of cyclic addition reactions, including the Diels-Alder reaction and 5+2 cyclic addition reaction, it's occurred in nature spontaneously or with some action of enzyme. Can you give some comment?
Yeah, I think that in nature it could be enzymatic reactions. That I actually thought about collaborating with groups developing enzymes to try to say if we can develop some enzymes for those reactions. But the enzymes are very substrate specific, I suppose. Yeah, and it can be very challenging if we want to design some artificial like enzymes for those reactions.
Maybe it's non-enzymatic reactions actually.
No enzymatic reactions, you mean?
Yeah, maybe.
Okay. Yeah.
So let me see, is there any other question?
Yeah, and I'd like to add here, they're actually very interesting that West group, they start the synthesis from nature species, isolated from nature, the furan sembrance.
Okay. If there are no more questions, maybe we will stop here. And thank you again for your nice talk.
Thank you, Professor Tang.
Yeah, so next we will welcome the last speaker for today's seminar, Professor Deng Jun. I will give a brief introduction to the speaker. Professor Deng Jun received his bachelor degree from Lanzhou University and a PhD degree from Shanghai Institute of Organic Chemistry, Chinese CISC, with Professor Liang. After a postdoc study with Professor Andrew Meyer at the Harvard University, he came back to China and joined in the Kunming Institute of Botany, Chinese CIS, in 2017. 3 years later, he moved to Nankai University, where he is now a professor in the Department of Chemistry. His research mainly focuses on the chemical synthesis of chemical emulation of the biosynthetic pathway of natural products, total synthesis, and as well as medicinal chemistry. Today, Professor Deng will give his talk with the title Chemical Emulation of the Biosynthesis of Natural Products. Welcome, Professor Deng Jun.
Okay, hello everyone. I'm Jun Deng from Nankai University. I guess you can see my screen now. So I thank Professor Tang for your kind introduction and Dr. Xiao's invitation. It's truly an honor to be part of this Thieme webinar, and I really enjoyed the talks today. It's also a great honor to serve as a guest editor of this special thin letter cluster. So, let me see. So as introduced by Professor Tang, I sincerely thank all the researchers of this area to contribute to this great cluster. If you are interested in recent progress of biomimetic synthesis of nature products, please find the related papers in thin letter. With the continuous advancement of methodology, synthetic chemists theoretically have the capability to synthesize any target molecule, given sufficient time and resources. However, the synthesis of complex nature products is still challenging, and the overall efficiency often falls short for in-depth biological studies. Therefore, our primary objective is to streamline the synthesis of these intricate nature products, and hopefully, by simplifying their synthesis, we can generate enough samples to facilitate extensive biological studies. So as we know that biomimetic synthesis is an effective strategy to streamline the synthesis of complex nature products, there are a number of successful stories in this regard. So the most well-known example is Robinson's synthesis tropinol about 100 years ago, which marks the dawn of biomimetic synthesis as ever. So our strategy is chemical emulation of the biosynthetic pathways of complex nature products. As you can imagine, there are two prerequisite steps for the chemical emulation of biosynthetic pathways. Firstly, we need to propose a plausible biosynthetic pathway, either based on a well-established biosynthesis or on our own speculation. So we believe that a well-founded biosynthetic hypothesis can serve as a valuable template for synthetic design. Secondly, we need to translate the biocatalyzed transformations into chemical reactions. The powerful synthetic chemistry could be used as a tool to mimic the biosynthetic processes. However, in most cases, the biosynthetic pathway for complex nature products is still unknown. And more importantly, there's a great challenge of translating enzyme or non-enzyme catalyzed transformations into chemical reactions. So overcoming these challenges is crucial for successfully emulating biosynthetic pathways in the laboratory setting. So as illustrated in this slide, we have successfully completed the total synthesis of several complex nature products through the chemical emulation of their biosynthesis. Today, I'll present our journey to cytocharsons. So let me give a brief introduction of cytocharsons. They represent a vast family of fungal metabolites comprising over 500 members. True to their name, cytocharsons exhibit a wide range of biological effects, including anti-cancer activity achieved by targeting acetine cytoskeleton and affecting various cellular processes. So typically, cytocharson possesses a tricyclic structure with a macrocycle spanning from 11 to 15. In recent years, Chinese phytochemists have discovered a series of downstream metabolites of cytocharsons, which we named them pentacyclic cytocharsons. These compounds have piqued the interest of many groups, such as Professor Tang, chair of today's symposium, and Professor Dr. Joner from University of Pennsylvania, and Professor Baustin-Ney from France, and our group, due to their captivating structures and unique bioactivities. So in addition to pentacyclic cytochasins, a series of cytochasin trimers and tetramers were also discovered. As you can see, these structures are exceptionally complex, and there are significant variations between different members. Most importantly, these compounds have displayed promising anti-cancer activity by activating capsid 3 and degrading PARP. The most complex one is this tetramer, asparflavine A, while asparflavine B contains a unique furan structure. Due to their extremely low nature extraction yield, there's an urgent need to develop efficient synthetic route to address the supply issue and provide a platform for subsequent anti-cancer drug discovery. As you know that after long-term evolution, nature synthesized various secondary metabolites from a common precursor to maximize the number of nature products, thus generating and retaining chemical diversity at low cost. At the beginning of this project, we were thinking if it's possible to design a K intermediate that could convert to both pentacyclic cytochasins and mineral cytochasins. If we are fortunately enough, in this way, we can establish a universal platform to achieve the synthesis of more than 500 family members rather than targeting a specific one. The challenge for this idea is the biosynthetic relationship between the containers is still unknown, and how to realize the biomimetic transformations. So first things first, we conducted a biosynthetic analysis of all the members in the pentacyclic cytochasins. Despite different oxidation states of functional groups on their core framework, we anticipate that all these pentacyclic cytochasins might be downstream products of asparagines D. This happens after a series of reactions involving carbon cation-driven pre-cyclization and in-cyclization. So as a first step towards synthesize the entire family, in 2018, we established a streamlined and effective approach to producing the K monomer aspartame B. This was achieved by combining 3 components of comparably complexity. So with this robust approach, we were able to easily produce substantial quantities of this K monomer aspartame B in diagram scales, ready for subsequent transformation. So based on our biosynthetic analysis, we successfully carried out divergent synthesis of more than 10 pentacyclic cytochasins from this shared precursor. We also revised 4 existing structures and confirmed the proposed biosynthetic hypothesis through chemical validation. Due to time constraints, I will focus on introducing the key steps of our synthesis of these 3 targets. So the first one, asparagine PZ, was first accomplished by Professor Larry Overman in 25 steps by means of a pre-cyclization and a Diels-Alder reaction. So guided by the biosynthetic analysis, asparagine PZ could be easily obtained in 1 step from asparagine D in quantitative yield. For another 2 molecules, we assumed that asparagine Z as a biosynthetic precursor for trichoderma A and trichoderma. We were able to synthesize asparagine Z in sufficient quantities by using our developed protocol. So additionally, with the use of a hydrofluoric acid as a promoter, we could easily transform asparagine Z into these 2 key intermediates through pre-cyclization. So when it comes to the synthesized trichoderma A from compound 25, the most challenging part was creating this tetrahydrofuran ring. Picture this, there are several transformations when necessary. First, stereoallylic oxidation was performed to form this tertiary alcohol. Next, oxidation of this amine to form an in situ imine. And this imine was trapped by this tertiary alcohol to form this tetrahydrofuran. So after extensive experiments, we managed to achieve this transformation through singlet oxygen-in reaction, followed by subsequent HAT cascade reaction. Later, Professor Bastenev also accomplished the formal synthesis of trichotyrone A based on this efficient transformation. So when it comes to the synthesized trichotyrone, the most challenging part is the formation of this alpha-beta unsaturated lactone. As we know that many methods for lactone dehydration reaction have been developed, but they all require the formation of lactone enol, which necessitates basic conditions. This proves to be problematic when there are more active ketones present. So based on these challenges, we need an orthogonal method that could convert hemiacetal 27 to alpha-beta unsaturated lactone without affecting the more active ketones. So luckily, we've achieved this transformation through photooxygenation and the ferrous ion catalyzed dehydration cascade reaction developed by Professor Tong and Wu. We successfully converted the dihydrofuran 29 into trichotyrone with 81% yield. It's worth noting that the biosynthetic pathway for the trichotyrone A and the trichotyrone haven't been proposed yet due to their unique structures. So considering the concise synthesis and mild conversion conditions, this oxygen-in reaction and the subsequent HAT cascade reaction likely represents the biosynthetic pathway for them. During the synthesis of these pentacyclic cytotransins, we found 4 structures were misassigned. We revised their structures through the combination of NMR calculation, biosynthetic pathway analysis, and the total synthesis. Professor Ben Chan has delivered a really wonderful talk about this part. I will not go through the details about this part. So the challenge for these parts are how to find which sterol center or which molecule is misassigned. What we found is that biosynthetic analysis played a central role in structure revision. For example, based on our understanding of the biosynthetic pathway and the results we obtained from our synthetic endeavors, we reached the conclusion that when this CD ring is formed through epoxide opening with this alkene, it adopts a trans conformation. So applying this principle, we began to question the structure of these 2 targets and revised their structure through a combination of NMR calculation, biosynthetic pathway analysis without synthesizing them. Then we tend to structurally more complex merocytotransins through detailed biosynthetic analysis. We propose that all these 5 subtypes of merocytotransins are biosynthetically formed through a Diels-Alder reaction and also quinone 5+2 cycle addition of acetylcholine and the monomer aspartame D. So due to time constraints, I will briefly highlight the key steps of our synthesis. Take aspartame A as an example. This sandwich type primer could be assembled through Diels-Alder reaction and then intermolecular also quinone 5+2 cycle addition. So this alpha hydroxy also quinone could serve as a diene to dimerize with electrodeficient double bond, furnishing the 5+2 adducts as per Galen A, along with its residual isomers. So by changing the components of both diene and dienophile, we can access all 5 subtypes of merocytotransins through also quinone 5+2 cycle addition. Although there are residual isomers in this reaction, the facial selectivity is specific and only endo duct were observed. This versatile approach allowed us to explore the diverse structure space of myelocytochasins effectively. So biosynthetically, as per Galen's A, was believed to be a 3+2 cyclization product of intermediate 7 through an intramolecular microaddition of this double bond and the subsequent aldol reaction cascade. However, this compound proved to be extremely sensitive to bases. So on the basic conditions, it's underwent a ritual 5+2 cyclization reaction, leading to the formation of triphenol. So after extensive experiments, we successfully achieved this transformation through a light promoted intramolecular 2+2 of this double bond with this double bond, and a subsequent alpha hydroxy ketone rearrangements. It's noteworthy that alpha hydroxy ketone rearrangement is typically employed to convert 4,6 bicyclic ring system to 5,5 bicyclic system, as demonstrated in previous studies. However, to the best of our knowledge, this is the first example of converting a 4,6 bicyclic ring system into a 3-to-1 bridged bicyclic ring system without the formation of a 5,5 bicyclic ring system. So by taking advantage of the biomimetic strategy, we have successfully synthesized the 10 different myelocytochasins in 4 to 5 steps, starting from as per Charlson D and epichlorine. Although some synthetic products, such as compound 7, have not been isolated from nature yet, we believe that they might indeed be genuine nature products. So in summary, we have accomplished the chemical emulation of the biosynthesis pentacyclic cytochasins and myelocytochasins by late-stage diversification and dimerization of a common precursor. This strategy sets up a general platform for the efficient synthesis of more than 500 complex cytochasins and provided chemical evidence to support the biosynthetic hypothesis. So finally, I extend my heartfelt gratitude to all the collaborators and graduate students in our group. Their dedication and hard work turned what seemed impossible into reality. We are also immensely thankful for the financial support provided by National Nature Science Foundation China and Nankai University. Thank you all for listening, and I'm glad to answer any questions or concerns you might have. Thank you.
Okay, thank you very much for Deng Jun. I think you gave us a very striking and beautiful biomimetic synthesis of natural products. Actually, I don't know there is any other way we can make this complex molecule with such high efficiency and concise. So this is the beauty of biomimetic synthesis, I think so. Yeah. So
Thank you.
let me see, there are any questions from the audience? Okay, I just have a quick question. As you know, these natural products are all derived from one common precursor. I just wonder how nature make this compound with just without the enzyme catalyst, they can make so complicated molecules. How do you think about this?
Yeah, it's really a good question. I have to say that in some cases, in our hand, I think we cannot transfer to realize this transfer without the assistance of like a extremely high temperature or other catalyst. So we believe that some conversions enzyme involved. But for some transformation like this one, I think probably it came from like a non-enzyme catalyzed process.
Yeah.
Another
So,
part, I think, for the oxidation of triphenol, we believe that so far, in some cases, this type of 5+2 cycle addition, there are some enzymes involved because the product is in entirely pure. So
you mean for some 4+2 reaction?
It's
should
not
be
for
catalyzed by enzyme.
enzymes. We found some examples, although the enzymes have not been found, but it's not in this family, it's other family.
Okay.
We found that it's formed through intermolecular 5+2 addition, and the product is in entirely pure. So we believe that there are some enzymes somehow involved.
Okay, so just to follow this question, you mean actually there are some enzyme can catalyze for a 5+2 cycle addition? Maybe not in this case, but in some other case.
I believe so. Actually, there are some groups in like they're doing this project. They're trying to identify which enzymes to catalyze this reaction.
Okay. Yeah.
Actually,
yeah.
actually, I have a little comment for this one. Actually, Professor Tang pioneered the synthesis of pentacyclic cytochasins. So we got a lot of ideas from your paper. So
Okay, thank you very much. Yeah, actually, I think this family of compound has been studied by your group very well. I don't think there are any other people can work on this same project anymore. Yeah.
Okay. Thank you. They still have a lot of different members in this family, so you are welcome to do the similar research here.
Yeah. So since you have, I think you got a lot of net products in this work. Do you have tried to do some medicinal chemistry or some biochemical biology study with these net products in the future?
Yeah, it's a good suggestion. So we are always planning to do that, especially like a chemical biology to identify which specifically which protein were binding with these unique nature products. But so far we haven't started. Hopefully in the next few years I can report the progress in this part. Yeah, thank you.
Okay. Another small question. How many students work on this project? Because actually I think it's very challenging work to make such amazingly complex net products.
Yeah, it's a good question. Actually, there are at least, I think, basically we have 3 students like Xianwen, Wu Han, and Ding Ming. And we also have like other students involved to cooperate with them. But mainly these 2 parts were done by these 3 students. This one, now he's a postdoctor in our group.
Yeah, it's a very tough work because before you can make the targets, you have to spend a lot of time to make the starting material. Usually take maybe 10 steps or 15 steps like that.
Yeah. It's true to persuade them to do this hard project.
Yeah, it's hard work for you to persuade them to do that.
Yeah. That's why I said it's their dedication turned what seemed impossible into reality. At the beginning of this project, even myself, I cannot imagine we can finish the most complex one. So I should thank all my graduate students and collaborators, and also Professor Tang. Thank you.
Okay. Let me see if there are any questions from the audience. Yeah. Okay. If there is no more question, maybe we will stop here. And before I close the seminar, I would like to thank all the three speakers for this seminar. I think all of us have learned a lot from your beautiful works. And Dr. Chai, could you give a closing remark for today's seminar?
Thank you. Yeah, sure. So thank you, Professor Tang, for chairing this seminar today. And I think from these complicated structures, I believe it is indeed very challenging to solve the problems of nature products. And I really enjoyed all the lecture today, and see it is really smart to using biomimetic methodologies to solve such problems. And I believe all these attendees can also learn from these lectures, and hopefully they can also inspire you in your future research work. Then thank you again for all the three speakers, Professor Chen, Professor Tang, and Professor Deng, and also the chair, Professor Yefeng Tang from Tsinghua University. And I encourage all the attendees to subscribe to our Twitters, our newsletters, and also the Cheminar series. The recorded Cheminar today will be sent to you soon. Yeah, so thank you again for joining this Cheminar, and I hope you all enjoyed a lot. Yeah, so have a nice day, have a nice afternoon, have a nice evening. Yeah, thank you. Bye-bye.
Okay, thank
Thank you
you.
for having
Bye.
us. Thank you.